Hi everyone. This is the second video on genetic algorithms with Abaqus and Python. So the first video we looked into how to create the model that we're going to use in this series of videos, but we didn't cover anything about genetic algorithms, which is just a classic Abaqus and Python video. What I want to do today is to start scripting the genetic algorithm and tell you exactly what is the idea behind these methods and how exactly you can script it in Python. And we're also going to go through the theory, but very broad spectrum of it, because it will make a lot more sense once you watch the entirety of the videos. And then maybe we can look into the theory once again at the end, because I think it's easier once it's all done. So before we continue, I just want you to understand that I'm going to be scripting this specific code that we've done in the previous video, but I actually have a script already, which is this big one, that does the genetic algorithm. So if you're a user of genetic algorithms, and this is one of the things that as a Python user, I want you to understand that once you code something, you don't have to worry about it anymore. You can just copy paste it into a new file, reorganize it a bit to fit the needs, but it's not necessary that you actually look into every single function, which is what I'm going to do in these next few videos. So I have a few functions here that I'm going to copy paste. Most of them are about genetic algorithms like this to create the initial population, to convert chromosome to data. So this is specific to genetic algorithms, and some other folders are more for housekeeping, like create folder, save in Excel, make a plot. So these things is just easier to read when you reorganize them as a function, but you don't necessarily need to have this in your code. It depends on the application. So I guess we can start. And to start, I just want to go through this image with you once again. So if I paste this image here, I just want to look through this with you very quickly so you have a basic idea of what genetic algorithms, what do they do. So it's a cycle, and it's a cycle based on the theory of evolution of species. And the idea here is if we let, in this case, animals, turtles, giraffes, whatever you want, or in our case, slabs with support conditions, if we let them compete for, let's say, food and mating, the most fit individuals will survive, and then they will create offspring that then will take the DNA from the parents that were already fit. So the idea here is if you run this cycle, many times, you will get the optimal solution by means of this comparison with biology, okay? What we're going to be doing is learn how to code these steps. So the first thing we're going to learn how to do is to start an initial population. So that one is pretty simple. Then we're going to find a way to evaluate each individual. This is where Abaqus comes in. So this is where the model that we run is going to be evaluating each individual. Then selection is actually pretty straightforward. It's just selecting one of them. Then we're going to make them have babies, and the babies could also suffer a mutation, and then the mutation gets fed into the population, and then obviously it won't be our initial population, will be the population after generation 1. So if you keep doing this over and over again, and we run it, let's say, for 100 generations or 25 or 15, it depends on the application how many we need. And also, it depends on the application how many specimens we have in each population. So I guess what I'm going to do is 100, and probably generation, I'm going to start with maybe 20. So it's going to be 100 specimens in the population that will run 20 times this cycle. And hopefully when we get to the end of those 20 cycles, we get the most optimal position for the columns. So that's the basic idea of genetic algorithms. And again, we can explain this in more detail once we get to the end of the videos. Now, one of the things that is very important to understand here is the necessity to work in binary. So I'm going to call this video probably binary encoding. So we need to figure out a way to write the DNA of each one of our structural specimens in a very simple way. If you think about the DNA of humans, of horses, of any animal, it's actually pretty simple. It's very long, but each building block of the DNA is very simple. You only have 4 options, A, T, C, and G, and they only pair with certain ones of them. So they are not complicated building blocks. And this is something that you need to understand here. It's much easier to work with simple building blocks that we're going to learn how to do today in this binary encoding that with the complicated ones. Okay, so this binary encoding goes in opposition to what we call our decimal system. So it's very important to understand how decimal system works, so then you understand how we are going to transform from the decimal system into the encoding. So for example, if you think about all the numbers we have in the decimal system, obviously we have the numbers 0, 1, 2, all the way to 9, which means that with one digit, if you only use one digit, we actually can write 10 different numbers. And those 10 numbers are 0, 1, 2, 3, all the way to 9. If we have two digits, we can write from 0 to 99, so that means we can write 100 numbers. If we have three digits, we can write 1,000 numbers, which is from 0 to 999. Now, the only reason why we use a decimal system is because we have 10 fingers in our hands. You don't need the 10 digits, the 10 options, to have mathematics, right? You can write this specific thing in binary. So another thing we need to think about is how do we go from one number to the next? So if we are working with one digit, as we just said, we can write 10 different numbers, 0 all the way to 9. But once we get to 9, what do we do to get the next number? To get the next number, we run out of digits, right? Because we don't have any other way to write 10 without using two digits. So, but how does that work? So we reset the count on this first digit, right? So it goes from 9 all the way to the beginning to 0. And then we add another digit, in this case starts at 1. And now this is very simple. So if we want to know the number next to 10, we just add 1 to the last digit. Eventually we get to 19, and the same thing happens again. So when we go to 19 to the next step, we go back into the beginning and start at 0, and then we move 1 to the other number. So same thing happens when we get to 99. So we run out of numbers to get to the next one. So we restart this at 0, restart this at 0, and then we get another digit. So then we can write the number 100. Okay, so the same thing happens in binary. So if we think in binary, we only have two options. It's 0 and 1. There's no other numbers. There's just these two. So if we use only one digit, we can actually only write two numbers, which is 0 and 1. So if we go to two digits, we can only write 4 numbers. And if we go to 3 digits, we can only write 8 numbers. So the logic here is, in the decimal system, if we have n digits, we can write 10 to the n numbers. And here, if we have n digits, we can write 2 to the power of n numbers. And the same thing happens, so similar to the decimal system, the same thing is going to happen now in the binary. We can write number 0, we can write number 1, no problem. But if we want to go to the next number after number 1, we cannot write the number 2, right? Because we don't have it. So what we have to do is reset the count on the number on the right, and then add 1 to the other one. So 10, in this case, would actually be equivalent to number 2 in our decimal case. We go to the next number, and then same logic. The 0 becomes a 1, and that stays a 1. By the way, see now how we can write 4 numbers only using 2 digits? So this matches with that. And now when we get to 11, 11 would be equivalent to 3. We're going to try to get to our next number, but again, we cannot write number 4. We don't have that. So we're going to restart the count here, and then add a number 1. And this will be the equivalent to number 4. And then same thing will happen until we get to 111. Actually, let me do this slowly. So this will be 101, then 110, and then 111. And this will be 4, 5, 6, and 7. Okay? So this will be 0 and 1. So as you can see, with 3 digits, we can write 8 different numbers, okay, from 0 to 7. And this is what I described here. Now, it will be a little bit frustrating if we're trying to guess how can we convert from binary into decimal, right? Because we're going to need our numbers in decimal to plug it into Abaqus, right? We just coded everything in decimal, so it would be quite annoying to have to recode everything in binary. So what we're going to do is just convert from one to the other. And how do you convert? So let's think about, for example, the number 737. How is this broken into pieces? The way this works is the first number is multiplied by 10 to the 2, and 10 is our base of the system. Then the second number is 3 times 10 to the 1, and the last number is 7 times 10 to the 0. So what you get here is 700 plus 30 plus 7. Okay, and that's how you get 737. So how do we convert binary into decimal? So it's the same logic. If I give you a random number, let's say 101101, and I want to write this in decimals, the way this works is our first number here, 1, needs to be multiplied by 2 to the power of, so this is 0, 1, 2, 3, 4, 5. So 2 to the power of 5. And then the next one plus 0 times 2 to the power of 4 plus 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1, and then finally plus 1 times 2 to the power of 0. So now if you want to get this number, so these are 0, that's 0, and that is 1. This one here is 4, this one here is 8, and that would be 16 that it got 0, so this one is 32. So if I add all this up, I can find out that that specific number in binary would be the equivalent of 45 in our decimal case. So we can confirm just very quickly that with 6 digits, we're allowed to write 2 to the power of 6. So that would be 64 numbers. So it makes sense that 45 ended up being the number that we needed here. So 45 is in between 32 and 64, which is a good sign. And just, I guess, as a test, if we think about the number 1, 1, 1, 1, 1, 1, this should be equivalent to number 64. So if we think about it very quickly, that will be just 32 plus 16 plus 8 plus 4 plus 2 plus 1. And let's make sure this is correct. So 48, 56, 60, 63. So actually this is number 63, not 64, because 0 also counts. Okay, so 11111 will be equivalent to number 63, although we can write 64 numbers because of the number 0. Okay, so I'm happy with this, and I hope this made some sense, how we work with binary and how we convert from one to the other. And this is precisely what we're gonna code in our script. We need to figure out a way to write this down, so then we can write our initial population with a much more simple numeric strategy, which is in binary. Because this simplicity is going to make our genetic algorithm a lot more easy, so then we can do all the other stuff that biology does, like selecting, reproducing, mutation. This is going to be much easier to do if we have our problem written in binary. Now, one final thing is, how do we deal with variables that have a different starting point than 0 and a different ending point than, let's say in this case, 64 or 32 or 16. So let's say, for example, we want to study different spans of beams, let's say. And let's say we want the span to be, let's say, between two numbers. Let's say between 1,000 millimeters and 10,000. Actually, let me give a more random number, maybe 12,000. So we want to study different beams, and they have different spans of 1,000 and 12,000. And we want to study all the spans in between. The first thing we need to understand is, if we want to convert this to binary, the 1,000 is going to be the equivalent to our number 0. So if our binary is 0, 0, 0, 0, 0, 0, that will be the equivalent of the number 1,000. And the same logic applies here to number 12,000, is we want this to be our number 1. So if we only use one digit, and again, with one digit, we only have two options. Basically, we are only allowed to describe the number 1,000 and the number 12,000. And we cannot choose anything in between, right? Any number that would be in between these two, we can't write it. It's just these two numbers. So think about a different option. Think about 10 digits. So with 10 digits, the first thing you need to remember is, if we have 10 digits, we're allowed to write 2 to the power of 10 different numbers. So the same logic will apply to the number 1,000. So the number 1,000 will be 10 number zeros. That will be the equivalent to number 1,000. And the same logic applies to number 12,000. It will be 10 number ones. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So when we're full of zeros, it's the number 1,000. When we're full of ones, that's the number 12,000. But now we're allowed to use the numbers in between. So for example, if we give the number that is right in the middle of these two, we would be able to write the span that is in the middle, which should be 6,500. So another thing that we can do with 10 digits is we can subdivide this space 2 to the power of 10 times. So 2 to the power of 10 is 1,024. So we're allowed to write 1,024 numbers to describe different spans. So we're going to subdivide these pieces into a certain spacing that then gives us 1024 different spans. So one of the first things we can say is, what is that spacing? So the spacing will be nothing more than 12,000 minus 1,000 divided by 10,024. That will give me a spacing of 10.74 millimeters. So if we think about it now, we know that the number 0,00000, this number here, corresponds to 1,000. So now we can start thinking, okay, what is the number 0,000,000,000? So that's 9 zeros and then a 1 at the end. That's nothing more than 1,000 plus the spacing that we just determined, plus 1074. So that will be 1010.74 millimeters, okay? So because we're using 10 digits, that actually allows us to study many, many different spans and study it very detailed, the space between 1,000 and 10,000. If we use less digits, let's say 9 or 8, this would start going up, and then it depends on the application that you're trying to do, what is the spacing that is necessary for you. But now let's say if I give you a random number, let's say 0,0,10,10, that's 6,0,0,0,0. The way we do this is, we know that's still 1,000, that's our starting point, and now plus 10 to the 74 times the equivalent in the decimal of this binary number. Okay, which in this case, if we are careful, that's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. This is 2 to the 5, and this one here is 2 to the 7. So if I do it in the calculator, 2 to the 7 plus 2 to the 5, that will give me the number 160. So that means that specific binary code will match with the span of 2718.4 millimeters. Okay, and that's it. I hope this made some sense. It took a while to explain, but this is very important to understand genetic algorithms because, as I said, the ability to write in binary is super important to make this work. And this is exactly what we're going to code today. If I go here to my script, I have my coordinates written in decimals, but I actually need to start transforming this. So we have 8 different parameters in this problem. So it's the coordinates of 4 columns in the 2 directions, x and y. And let's say I want for all of them my initial to be, let's say, 200. And the reason why I'm choosing 200, if you remember, I gave the dimensions of the column to be 300 by 300. So if I start at 200, I guarantee this is inside the domain of the slab. So it's a little bit of a hack, but it's much easier just to do it this way than figuring out the errors that can come with Abaqus. So we're going to say that we want the initial to be 200, and we want the final to be either the length or the width, depending if it's x or y, minus 200. Okay, so I want the columns to be able, and let's see if this makes sense, I want the columns to be able to start at the position of 200 and to end at the position of 6,000 minus 200. Okay, so they can't stay in any position between these two numbers. And then the next thing we need to think is how many digits, and this is not my final code yet, I'm just explaining it, how many digits do I want to use to describe this variable? Okay, so let's say in this case we're going to use 6. Okay, so I have some code that I'm going to fetch now. So I'm going to get this code here, and I'll change it in a second. And then I'm going to get this function here called chromosome to data. And since I have time, we're going to talk as well about this initial population function. So then we have a little bit of everything we need for our script. So this first variable that I have here, I'm going to call this x range. And x range is going to start at 200. That's going to be put in that first box. It's going to finish at length minus 200. And then in this specific case, I'm going to keep 6 as well as the number of digits for the coordinates in x. And now for the coordinates in y, I'm going to do the same. I'm going to start at 200, finish at width minus 200. And then I think I'm going to give it 6 as well in this case. So what is the initial population? Initial population is going to be a series of numbers where I get the necessary information to build a model. Now, so if I have 4 columns, and I need 6 digits to describe the x coordinate, and I need 6 digits to describe the y. Let me change this to 5 actually, just to give it a little different. So 6 digits to define the x coordinate, and 5 digits to define the y coordinate. I need 11 digits just to describe the position of the first column. Okay, so at the end, I actually need 11 digits for this, and then 11 for this, 11 for this, 11 for this. So I'm going to end up with 44 zeros and ones that then will represent these parameters that I just described. So what the initial population does is basically give me a list of genetic codes that have 44 numbers in length, and then you have a certain population size that I'm going to define. So as I said, I'm going to say the population size is 100. That's great. And then the variables, I have no idea how this works, so give me a second. Okay, so I understood how this works. So what I'm going to do, so I need to define the number of columns that I need. So number of columns. In this particular case, we're going to go with 4. And I want to say that for I in range of the number of columns, so I'm going to run this 4 times. I want to append to my variables list, I want to append the x range, and then I want to append the y range. So what this basically does is takes this list here, 200, length minus 206, and it's going to append it to variables, and it's going to do this 4 different times. Actually, to explain this a little bit better, let me open another version of Python so then we can see what this is doing. So I just opened here my Spider. Spider is just another Python that is a bit more user-friendly than Notepad++ because you can actually run things straight away and see what they're doing. So I'm just going to show this to you so that this makes a little bit more sense. So if I have my x range and y range, and by the way, this is going to be commented because we don't need this anymore. This was just for the first video to make sure this was all working. Now it's going to be the genetic algorithms that is going to give us the coordinates of the columns. So this is going to be commented. So if I copy all this, and I need that number of columns equals to 4 as well, I think. Actually, I might need all of this. And I'm just going to paste this here, delete this part here, and see what is this complaining. Okay, there's 2 dots missing there, which is going to be a problem as well. So let me do that. And now let's run this. So I'm happy with this. I can go now to the variable explorer. Here we have, as we said, the length is 6,000, the width is 5,000, number of columns is 4. So then I have x range and y range is nothing more than these 2 numbers. So the initial point is 200, final point is 5,800, and 6 is the number of digits. And then in this particular case, that's 200, 4,805. And then population size is 100. I don't know if this is needed just yet. Variables is empty. And then what this does is for I in range of the number of columns. So for each one of the numbers until we get to 4, append x range, append y range. So variables will just be these 8 variables that are described by this 8 list. So the first one we know is the x of the first column, so 200, 5,800. Second one is the y of the first column. Then is the x of the second column, y of the second. So x3, y3, x4, y4. So basically what I'm doing here is finding all the variables that I have in my problem and writing them in a list called variables. And then this is going to be plugged in into this initial population function. So I'm going to copy just this bit here, so then we can see it in action in Spider. And then if I make any changes, I'll change it on the other side. So what this does, it starts with a count that is equal to 0. Maybe I need to zoom in this a little bit. There we go. So starts with a count that is equal to 0. The initial population is an empty list, and the length of the chromosome. So chromosome, I'll show you what a chromosome is in a second. It's just a fancy way to call a list of zeros and ones. So the length of the chromosome for now is 0. So for I in variables, so the variables are going to take all these 8 lists, okay, one at a time. The first thing is the length of the chromosome is the length of the chromosome as it stands. So it starts at 0, and then it adds I2. Okay, so this makes sense. So if I go into the variables, and I is each one of these numbers, I2 is just the 5s and the 6s, is the position 2 inside each list. So that's position 0, position 1, position 2. So what chromosome length will be is just 6 plus 5 plus 6 plus 5 plus 6 plus 5 plus 6 plus 5. Okay, that's what this for loop does in line 27 and 28. Defines what is the list of the chromosome, what is the length of the chromosome. And then For number 29, it says, if the count is less than population size, so the count starts at 0, and if you remember, the population size is 100. So what this will do is to say the chromosome is empty, is an empty string, and for I in range of chromosome length, so it's going to do for each point in the chromosome length, it's going to say the chromosome is whatever it is, plus a random choice between 0 and 1, okay? So this is making sense. So it's just going to select randomly, and I need to import random for this to work. It's just going to select randomly a 0 or a 1 and going to add it to the chromosome. And once this is all done, this has a little bit extra piece of code. When this is all done, it checks if the chromosome is already in the initial population. And if it's not, it appends to the initial population, and then the count becomes count plus 1. So what's the idea here? Otherwise, it prints repeated, which is not that interesting. So if we run it, hopefully this will run, we're going to end up with initial population, as you can see here, which is a random list of zeros and ones. The length of each one of them is ideally 11 times 4, so 44, 6 plus 5, 4 times. And it's just random lists of zeros and ones, and I get 100 of them, okay? And then the next step will be how do you convert this mess of zeros and ones into the decimal places so we can plug it into Abaqus. But I'm happy with this. I'm actually pretty happy with the code in general. So I'm just gonna say that this is very well done. Variables, population size, and this should run without any problem. Otherwise, we can fix it later. Then the next thing we're gonna do is how do you convert the chromosome back into decimals? That's what this function does, chromosome to data. So if I go here and I paste it, so let's have a look. And for this to run, let me push this back, and I need to delete this. So for this to run, I need a chromosome. So I'm going to say that in this specific case, just to run this once, chromosome, I'm going to copy one of these. So let's say the initial population in position 22, that's this chromosome. So I'm just going to copy this random list of numbers. That's going to be my chromosome for this example. And the var data is empty. Start is 0, whatever this means. Well, the start is at 0, so it's going to say we're going to start there in the beginning of the string. And then the variable in binary is the chromosome in position 0. Chromosome 0 is nothing more than what's inside this list, so it's going to be all of that. And then we're going to start at the start, which is 0, and we're going to finish at the start plus I2. So what's basically saying is the variable in binary is actually the first 6 numbers. Okay, and this is controlled again by this variables list here to say the first 6 numbers are this variable, the next 5 are this variable, the next 6 are this variable. So this basically is doing is splitting this in 5s and 6s, so then we can convert each one of them into decimal. So that's what this does, var in binary. Then var decimal is exactly the formula that I showed you here. So it's to find how you convert from binary to decimal is you need to find that number and multiply it by 2 to the power of the position of that number. Okay, so if you have a 1, that's 2 to the 5, then if you have a 0, 2 to the 4. So that's exactly what this does. Okay, there's a piece of code missing here, which I need to fetch it, which is the one that calculates the step. So I found the code already. Okay, so I just added a new piece of code that I needed. So the first thing I need is for each one of these lists, X range and Y range, calculate the step that we have with the number of digits. So that's just the final minus the start divided by 2 to the power of the number of binaries minus 1. So that's the equivalent of this example that we did here with the 12,000 and the 1,000, that we got a step. And since I trust the code more than what I did here, we probably need a minus 1 there. So it's probably not 1,024 number of spaces, it's 1,023 number of spaces, because if you have 1,024 numbers, you're going to have 1,023 spaces. So this number is a little bit wrong. It's not 1074, it should be a little bit bigger. And that's what this code is doing. It's 2 to the power of 6 or 5, and then subtracting 1 just to get that step. Okay, and then what I do is I append the step into my list of variables. So now this step is going to go there into the back, okay? So that means I'm going to study in X. The position is going to vary from 88.88 millimeters. That's the steps I'm going to use. And then 148 in Y. And finally, if I can do that, now this code should work. And what this does now is the variable in decimal is the starting point plus this is just that number to the power 2 to the power of that number, and then times the step that we have. So if we go back, is this step here of 10 to the 74 is the step, and then 160 is how you convert binary into decimal. So if I do that, then I can append the var data into a new list, and then the start becomes what it used to be plus this length. So now if I run this, what I just figured out was how to convert this chromosome, so this chromosome that is this list of ones and zeros, into this variable called var data, which has this 8 coordinates. And as you can see, they look pretty correct. So the first numbers, the first 6 numbers, so 101100, they stop there, are equivalent to 4111 millimeters. The next 5 numbers, so 10110, correspond in our case to 3464. So this will be the position of the first column according to this genetic code. Okay, and that's what Abaqus then comes in. Abaqus is going to take these numbers that we just did and is going to calculate displacements, whatever we need for our structure. So I think the video has been gone long now, so I'm going to definitely not include anything else in this episode. I'm just going to make sure this piece of code is in the right place. So this part that calculates the step, I'm going to place it. So we have our X range, Y range, and this goes here, calculates the step. Then population size 100. I'm happy with this. This does the initial population. I don't think I changed anything. And this does chromosome to data, and I haven't changed anything. So I'm happy with this. Hope this made sense as a first episode. So it's a long series of steps, and trust me, the other videos will be easier, or at least more intuitive. So it's a long series of steps on how to convert a series of numbers into binaries in zeros and ones, and then how to convert back the zeros and ones into the decimals that we need. Another thing that was important is how do you create an initial population? So you find the right chromosome length that we need, and then we create 100, in this case, different lists of zeros and ones that then will correspond to different rectangular slabs. Okay, then we're going to code the rest in the next video. So thank you for watching and have a nice day.